whom, of course, everybody knows, everybody appreciates his scientific achievements and his wisdom. And I guess we'll hear something about both of those in his talk. I was trying to figure out, Barry, how far back we go. I think it's...
I think an embarrassingly long time.
I think it's about 4.5 decades.
Yeah.
Anyway, Barry, over to you.
Okay, thanks. Okay, when I was asked to give this talk, I had no idea it was going to be the final talk of the conference. I'm not really prepared and don't want to try to review the highlights of the meeting. So I'm not sure exactly what I'm doing, but I gave a title early, which is Gravitational Wave Experiments and Future Prospects. And so I think where I'll fit in is somewhere between what you probably know pretty well and where Salvatore picked up on the long-range future of gravitational waves and LIGO. I'll comment on some other things as well. But probably if I have anything, I'm not going to have that much new to say that most of you haven't seen or heard somewhere, but maybe my perspectives on them have maybe a little value. So that's probably all I can try to give to you. So I think it's, everybody knows what has been seen in gravitational waves so far is binary inspirals. So that's basically the state of the art at the present time. The practicalities of doing that are that the black holes are heavy, so they give a bigger signal, and they were detected first. The neutron star binaries, we had a little more information on before we detected gravitational waves, having seen binary systems in our own galaxy. The difficulty was what fraction of them had been seen in our galaxy and how typical is our galaxy in predicting what we'd eventually see. But that was our target in setting the sensitivity goals of LIGO. We really couldn't predict what the black holes would be. We got lucky. They were easier. Of course, they're easier because they're heavier anyway. And the third one, of course, is black hole neutron star, which we presented as the last one we've detected with 2 examples in the last couple of months or month or so. The technique that we use is called match templates. And that technique is to actually calculate and to great accuracy what we're looking for. To do that, of course, and cover the whole regime that we might look for, it means calculating lots of waveforms that we compare with the noisy data that we have. We use a technique called match templates. And doing that, you can actually pick a signal up that's quite a bit smaller than the noise level. If you compare it with a known, it can be buried in the noise if you're looking over a long enough time that you integrate up a signal that has a certain shape. And that was basically what we have used. And except for the very first event seen in LIGO, which was the one that was the discovery event where it stuck up over the noise level, so you can see it without that, we've used match templates. You couldn't see the signals of most of what we've seen, or a lot of what we've seen, without doing the match template technique. To do the match templates, however, we have to be able to calculate what we expect. And that's always been a big challenge because we use general relativity, of course, to look at what would happen if we had an inspiral of any one of these. We have to calculate that a lot of times. So we have to use the computer. It took a long time to develop the technology to do it on a computer using numerical relativity, which we have to use to get the last part of the mergers. And so that developed in time for us to see them. But then we have roughly a few 100,000 templates that we compare with each time part of the data. That's how the signals have been extracted. And basically, we've seen all 3 of these now. And as we move along, it's to understand the physics that's involved in that. I'll comment about it just briefly. The second kind of source of gravitational waves that we should be able to see in a ground-based experiment like LIGO or supernova, or another burst signal might be gamma ray bursts, which we actually have seen in the sense of the first neutron star merger. But supernova, I'm not going to talk about those, but let me just again put it in perspective. When you have a gravitational collapse of a star, in order to give a gravitational wave signal, it has to collapse not 100% spherically symmetrically. So to the extent that it doesn't collapse totally spherically symmetrically, it can give a gravitational wave signal. We know that they don't generally, because when we have a collapse of a star, the final product, like a neutron star, tends to have a few hundred kilometers per second velocity going off. So it basically didn't just collapse. The calculations are hard to do because the calculations of a supernova are done on supercomputers, usually someplace like a big routines that are done at Livermore or somewhere. And they basically assume spherical symmetry in the first stage. So it's more phenomenological, the predictions that we have from supernova, and we don't have a good sense what the waveforms would look like. So we have to look for a kind of generic burst signal, and that limits the ability to do that too. In order to get a gravitational wave signal, there has to be enough supernovas, and to get a supernova once a year, you have to be able to see out to about the Virgo cluster. So our own galaxy has only had, one at the time of Galileo, and questionable after that. So if you really want in the lifetime of an experiment, we have to have a range out to the Virgo cluster. The ability to estimate how far we can see is unclear because of the lack of ability to actually do the phenomenology of the calculations of the collapse, but we look for supernovae. We haven't seen any examples, of course. The third kind of source, and the one that personally I thought would be the first we would see, but I didn't understand the problem well, is gravitational wave signals that would come from a pulsar, a neutron star, a pulsar in our own galaxy. These are very attractive because if we could see gravitational waves from a spinning neutron star, it keeps sending the signals. So in comparison to the gravitational waves we've seen, we could then study whatever one we found, even as we improve the detector, and understand a lot about neutron stars, for example, and maybe a lot about gravitational waves. The problem in doing that is a very difficult logistics problem that limits us. We look for neutrons. Of course, it's a big effort that we have. We look for spinning neutron stars in LIGO data, and we've set limits. In fact, what seems like pretty impressive limits, that there's no, let's say if you put it in spatial coordinates, that there's no mountains on a known neutron star that we pick that are bigger than a millimeter. But basically the problem is that the neutron stars that are well known because they're pulsars and they give us stable signal and we know where they are very old. And by being very old, they're very much more symmetrical than the neutron stars when they're first born in a collapse. So we look for known ones, but they're not going to give the biggest signal. And looking for the ones that were young and maybe aren't as stable and not known for the radio signals are a difficult problem because we have to search. We don't know where to look, so we have to search the whole galaxy, following around the ephemeral and trying to get the signals. That actually is a computing problem that's beyond our ability to do it. We try to help that by having a program called Einstein at Home, where people can give us cycles on their computer so they help us do it, but it's still, we're orders of magnitude from being able to, let's say, systematically cover the galaxy. So far we haven't seen any I keep thinking it'll be the next source we'll see. The last one is cosmological signals, of course, and that was a subject discussed at this meeting, and I'll come to that a little bit. Going maybe a step further is, are there signals of gravitational waves now that don't have, not only black holes, of course, don't, but we knew about black holes, that don't have electromagnetic counterparts, and so we don't know really what we're searching for. That's always been an intriguing and maybe important part of what you can do with gravitational waves, is use the expression always, it's a new way to look at the sky, and it is. So why shouldn't there be other kinds of sources that give gravitational waves and not necessarily are known from their electromagnetic signals? That's, again, a rather difficult logistics problem, and knowing how to approach searching for them. We search for them. We do what we call, we have a group that does it. We call it looking for unmodeled sources. In other words, we don't know how to model it like all the ones above, even though some of those we don't know how to model very well. It's no, what I do. At least we have some sort of sense what we're looking for. So here we try to find some technique that can look for, without biasing it too much, look for a waveform where we don't know what the waveform will look like. And there the best technique we have so far uses wavelets, basically a wavelet technique, a mathematical form that's pretty generic to look for signals. But of course, even using that, we make some assumptions about the form of the finite signal that would be seen. So we don't have a pure good way to just look at the sky and see that there's signals. Some of us have been working on whether we can use AI or machine learning techniques to look at LIGO data and look for some signal, looking at all the signals and finding things that are just different without having it biased by the bullets that I have above. And that's an ongoing project. So this gives you a sense of kind of the breadth of the groups that look at science in LIGO. Of course, all the focus has been on the first one, the chirp signals, and I'll talk about that just a little bit. So unmodeled, I just talked about. So far, people have seen that we've reported about 67 events, and in the second half, we've just released most of the data from the third science run. I'll make a comment here. You notice the way we run an observing run, and then we disappear for 6 months or a year or so. And then we come back and then we run again for a year. And then we're off. And so after this, and each time the reason this slope gets steeper is we've added new technologies. Salvatore mentioned that we use squeeze light to get into 3A. We made some other important improvements, like a higher power laser and so forth, that got us the higher rate by almost a factor of 10. And basically the strategies are quite different than CERN. So at CERN, except when you have a really major shutdown, like now to improve the detectors, most of what is done is limited by statistics. So that you want to run for a long time, be off for as little as possible. Our situation is quite different than that. You really want to be off a lot in LIGO if you can improve things, because an improvement of a factor of 2 in the sensitivity for, say, binary inspirals gives you a factor of 8 in rate, because the factor of 2, we measure an amplitude, not a power. And the factor of 2 gives us the fact that we look a factor of 2 further out in the universe. And there's a factor then of 2 cubed, or 8 more possible signals of the volume of the universe that we look at. So basically, gaining sensitivity is a very rapid change in how much we're able to see things also it moves us closer to an ultimate goal of seeing further out and seeing something other than its short, small redshifts, which we do now. So we would like to be, I would like us to be down a lot more than we are so we can make upgrades, but the pressure is always a kind of uninformed community and the NSF and so forth that wants us to take data to justify the money they give us, and so forth. So we run actually more than I think it's worth us running. We're down now. We didn't quite finish the third data run because the pandemic came and we ended a 1-year run after 10 and a half or 11 months. And we've been down ever since. We unfortunately didn't get as much done as maybe one would like during the time, the 14 or 16 months of the pandemic, because a lot of the work that we do and a lot of the work that we happen to be doing to do upgrades now needs people working in close proximity to each other. If we're working on the optics or things that require people to be close, we haven't been able to do it. So basically, we've lost almost a year of inactivity where we've tended to watch the lab, but haven't been able to upgrade. We're upgrading now, although it's slower because we can't work quite as close as we might. And we expect to start the fourth data run next summer. So, and at that point, we will improve another factor where the number of events that we expect will approach one a day. It'll probably be one every other day of the binary inspirals. Okay, so what do the events look like and what do we do with them? Everybody's familiar with this picture. It's a picture from the first event, but what I want to show is to point out the strategy is the first picture, the top row is the two signals from the two different LIGO interferometers in Louisiana and in Washington. And the second is the calculations using Einstein's equations of general relativity for the masses and so forth that we put in the paper. And the third one, the third frame, is the subtracted difference between the two. And what you notice is it's just noise. So that's the fact that the measurements aren't perfect. They have noise on them, but there's no sign of anything that isn't there. And it shows how well our data fits Einstein's equations. So this is only over half a dozen cycles, but the second event that we saw, which was only a few months later, had hundreds of cycles, and it fits Einstein's equations very well. So we're able to use Einstein's equations to look. There's a lot of information in these waveforms. So it's not quite like one event in particle physics. It's one event that you get a long history. This is a pretty short history because it was heavy enough masses that it never got it to frequencies that were very far above our threshold in LIGO. We're limited by the mass limits what frequency you can get to, and the frequency just got into our sensitivity band. But the chirp mass formula is the one I show, and there's a second term which I didn't show on here that we use to fit the data. And it gives us a lot of information. It gives us information just on one event, and looking at the waveform. It gives us information on the mass ratios, information on the spins, information on the redshift. The amplitude itself, as I said, is inversely proportional to the distance. The precessions and so forth are there, and we can measure. And then with the auxiliary information, like the strength of the signal, we get the sky location, the distance, and so forth and so on. So there's a huge amount of information that comes with these, limited by how good the data is, what the signal to noise is, and how many cycles there are, and so forth. So that's what we deal with. This is the second event, and I show it to you just to show you that we look in the second event, which was much earlier, we do now, at the different portions to see if there's any deviations, for example, from Einstein's equations and so forth. And so we analyze these events in great detail. This is a picture from a year or so ago before the third data run. And it shows the first 10 or so binary inspirals. And what you see, and all you should take home, is that the waveforms, the little inspiral forms are different for the different ones. And that depended on what the masses were of the two binary inspirals. And so we're collecting those. The main science issue for us, the main concentration of the science that we're doing with those is to try to understand their origin. What is the origin of these black holes? And I'll show you some distributions, but we don't have a good handle yet on that. But having information on the distribution of where they are, what their redshifts are, what their masses are, what their spins are, all this kind of stuff is maybe different if they're born from a star, or if they're somehow dynamically captured in some place in the universe, or they're primordial. There may be differences in them, and that's the kind of thing that we're investigating as we collect more data. The detector performance, in order to do this stuff, ideally you'd like 3 detectors that were performing exactly the same. That isn't what we have. In general, the 2 LIGO detectors have been the same for all the runs. In the last run, it wasn't quite, because we decided to turn back on when we had promised to in calendar time, rather than make them work the same. And we had made an improvement in Louisiana with a laser that we didn't have time to put in Hanford, Washington. So the top 2 are different for the last data run, but they're generally the same. We do have an issue that we have 3 detectors, but so far the Virgo detector is only about 1/3 as sensitive as the LIGO detectors. As I pointed out, when we see out into the universe that a factor of 2 in sensitivity is a factor of 8 in rate, which means mostly for, let's say, high signal to noise events, we don't get a signal, a substantial signal at the present time from Virgo. Virgo should have, when it's made to work as well as it could, it's comparable sensitivity to LIGO. It came on later and it's catching up. So we'll be better when we have 3 interferometers that are all more or less the same. The next data run, we expect to be, instead of what I have here, which is 45, 108, and 135, the 2 LIGO detectors should be approaching 200 megaparsecs. This is the distance by which we see an ideally circulating neutron star binary system, how far out we can look. And we just use that as like luminosity and an accelerator to tell us how far out we can see. So we'll be improved that much. It'll again improve the rate, as I had said. So we see all these masses. You can see that there's a tendency for us to see heavy masses just because they get bigger signals. So we have a bias toward that. But it was a big surprise to astronomers that we see so many heavy mass binaries, or that we even see such heavy mass binaries, because it's hard to fit that with heavy enough progenitors to make them, because very heavy stars are basically unstable, except if they're in some very low metallicity part of the universe or something. So one qualitative conclusion is that we see heavier black holes. As I said, our main emphasis now in collecting these has been trying to gather enough information on the distributions so that we can make conclusions about the how they came about. And that's happening. A second thing, not emphasized at this meeting, of course, that we do and are doing, is to test general relativity. So I showed it a little bit on the long signal from the second event, but we've taken all our events and we basically set limit on the parameters of GR. The ones on the left are the GR violating parameters using Einstein's equation for the inspiral coefficients. On the right is the post-inspiral, and we see no indications of a violation yet, or anything that doesn't fit Einstein's equations. Although we give numbers for that, it's hard to know how good we are doing compared to, say, alternate models of general relativity. And the problem we have there is that alternate models of general relativity that people suggest are not mature enough or carried to the level where we can make these detailed comparisons. So we search for violations of something not fitting as well as it should to Einstein's equation. So far, it all fits, but we can't tell from that we have eliminated a variance of Einstein's or alternatives, because those basically haven't been carried to the same level where we can compare and ask whether the data fits those or not. It's a little frustrating. We do try to see how sensitive we are by putting in a term that would change the waveforms. We put in a dispersion term. If you take one limit on the dispersion term, that would be the limit where there's a mass, or that gravity had a mass. Of course, Einstein's equations are classical. There is no mass, but that's the mass of the graviton. I may have missed, I saw on a slide 10 to the minus 23, and I may have written it wrong here. I don't remember what our limit is, but we have the limit on the graviton of 1.76, 10 to the minus, I think it may be 10 to the minus 23, and I wrote 10 to the minus 22. And as I point out, it's difficult to compare with alternate theories of general relativity. It's just a limitation in the way we have to compare data. The distribution of black hole events that we're looking at, this just shows you that on the right that there is a distribution in the masses and distribution in the we basically are looking at that to try to understand things, but we're also looking at extreme examples. I'll show that in a minute. And as we collect data, what's shown on the left is the cumulative collection of data scales, just like the ability to how far out we look in the universe. It scales like the volume, which is what's compared here. So there's no indication that everything's close or far away or anything at this stage, although we're not going very far out yet. So that's basically the scale. The other observation that we made, of course, is the neutron star binary inspirals. And that's shown here. The bottom graph is our time frequency plot from LIGO. In an earlier slide that I showed, because neutron stars are so much lighter than black holes, 1.4 solar masses, they basically go to much higher frequencies. So they stay in the LIGO detection band for much longer. And there, basically, we see thousands or tens of thousands of cycles, and they go, and the signal goes for seconds instead of tenths of a second or minutes. So it's there for a long time. What's seen in the bottom is the last part of the merger of the first neutron star binary, a time frequency plot. And you can see the line continued up to the time of the merger. And 1.7 seconds later, it was observed in the Fermi Satellite as a gamma ray burst signal, which started us to look at, to alert the astronomical community. A comment on this first. We expect that when neutron stars collide, the first thing that you'll see is the gravitational wave signal. Sometime after that, the nuclear physics effects happen, some unknown time after that. And so then you see a signal from the neutron stars. So the fact that they're not coincident is expected. You expect the gamma ray burst signal, which is gamma rays coming out, will be sometime after. It turns out it's 1.7 seconds in this observed event. But even at 1 second or so difference between the two, I should point out that this event, when we analyze it, is 150 million light years from the Earth. Being 150 million light years, that's 1.5 10 to the 15th seconds, and the time is the same to basically 1 part in 10 to the 15th. So the interesting thing, although we never questioned it, is that this basically demonstrates that the speed of gravitational waves and the speed of light are the same to 1 part in 10 to the 15th. Empirically, we've measured that. Looking at this event, we were able, because it was favorable over the Virgo location, so we saw enough signals from Virgo and from us to be able to isolate it in the sky pretty well, as you can see in the plot on the right. And it agreed with the Fermi graph. Astronomers had told me for years that we could never do multi-messenger astronomy because we couldn't point well enough. But interestingly, on the first event of multi-messenger astronomy, we pointed better than the astronomers did. So it's an interesting point. Once everybody looked at it in different frequency bands, what was seen is the evolution over first the 1.7 seconds when the gamma ray burst came, and then over time in the different frequency bands. And that fit quite well a picture of what's called a kilonova, the phenomenology of a kilonova. I don't have time to really go over that. But it's the first example of what we think is going to be a long-term important development for astronomy and astrophysics. And that's, I would argue, the biggest gain in astronomy in the last 50 years is the fact that they basically look at the same phenomena in different frequency bands. We do astronomy in everywhere from, low frequencies to very, very high frequencies in different ways. And the future is to do multi-messenger astronomy, what's called multi-messenger, and that is to look at what comes from these sources, not only in different wavelengths in the electromagnetic wave, but also in gravitational waves and neutrinos. And of course, the simultaneous observation of the neutron star system did the first two, where that signal wasn't quite strong enough to give a neutrino signal, although they looked. But in the future, seeing both the nuclear effects that give neutrinos, the gravitational effects that give gravity, and the electromagnetic effects that give signals in the various astronomical observatories will give us a very strong way to look at any phenomenon in the universe. So we look at doing that. We have a challenge experimentally to do that in gravitational wave interferometers. And that is, it's hard enough to identify gravitational waves with Einstein's equations and looking for mergers and so forth. And yet, in order to alert astronomers, we have to do it very quickly. And this is a real challenge, because if we do it quickly, but we're not very good at it, then we'll keep telling astronomers to look where we think we saw something in the sky. And then we have to afterwards say, whoops, we didn't really see it there. And so we spend a lot of effort, and there's a lot of clever developments that have gone into the ability to make a decision on whether we see a gravitational wave online in just a few minutes. And then we do a very intensive analysis after that to be able to tell them, no, we didn't really mean it if we don't. But the real stuff that you see in the literature takes us hours, days, weeks, months before we get real parameter estimations. The astronomers, of course, want some selection to know. They want to know as much as they can before they decide to turn telescopes or whatever it involves to look at our events. And that's a trade-off between us giving information that we don't know very well about the events or not. And that's a constant tug of war with the astronomical community. So this is an ongoing issue. We need 3 interferometers to point in the sky, and then we need to make tell them where it is, and then we need to make a very quick decision. We're pretty good at it. I think during that 03 run that I showed you, we made about 100 announcements or so, and the number of final candidate events is something like 80. So only 1 out of 4 times or 1 out of 5 times do we have to immediately tell them we didn't really mean it, sorry. So we're pretty good at it now, but we're working on it. We'll be better at all of this in the future. So we can look forward to being able to see gravitational waves with a better understanding of where they came from and so forth, because we're building a third LIGO. It'll work at least as well as the other ones because we can spend all our time making it work rather than taking data, which we're doing with LIGO itself. It has all the most modern developments as we develop them for LIGO in India. So we expect by about 2026 that we're running with 3 detectors in LIGO, and the best one I would venture to say should be LIGO India. We also have Virgo, and then in Japan, the Kagra detector is turning on. Yet is unclear how sensitive that'll be. They're very adventurous in trying to do cryogenics, and it's underground. So it's made steps that'll be very valuable for the Einstein telescope and learning how to work underground, and also cool. But those are both, especially the cryogenics, it's difficult to do. So we'll have to see how sensitive they end up being. They're turning on now. So hopefully we're officially adding them to the network, but it'll probably be a little time before they're up to speed. When all of these are on and up, we'll be able to see in the sky very well. If you look in the upper left, it's more or less the picture today of how well we can localize. We were very lucky on that neutron star event that we ended up in a portion of the sky where we could localize well. But by 2025, we should be able to have good localization essentially anywhere we see an event. So that's an important improvement that'll happen as we move through this decade. You can see what adding the third detector did when Virgo joined us. These long stripes are how well we could tell with just LIGO itself. And the GW 170814 was the black hole event that was seen very shortly after Virgo joined us in 2017. Just for numbers, we could only tell to roughly 1,000 square degrees where something was with LIGO alone. And we can tell to tens of square degrees, depending on where it is now, for events using Virgo and LIGO together. And in the future, we'll be able to do well enough to keep astronomers happy. I might say, except for one event that we had one report, which isn't confirmed, and all the 70 or so black hole binary events, there's been no electromagnetic counterparts that have been verified that are found. There's one paper that said they saw something at 1, which I may have time to mention. So localizing, I talked about. I think I'm going to skip a little bit because I'm going to lose time. That neutron star event, we had the fortune of basically the astronomers being able to locate what galaxy it came from. And I don't have time to talk about it, but basically that gave us the ability to, with an ambiguity on the spins, which we couldn't tell, to be able to actually measure the Hubble constant based on one single event. We all know that there's a tension, is the word they like to use, between the two different measurements of the Hubble constant. Hopefully that'll get resolved in the near future. But if not, when we collect enough data, we're a rather independent way of measuring the Hubble constant. I think in any real sense, that means 2030 or something for us to get enough data to be able to have our independent measurement of the Hubble constant. This is just the kilonova picture, but I'm going to skip that because I want to cover some other things. I mentioned, but didn't give any results because we don't have anything really definitive, that we're looking at all the distributions of the black hole events in order to try to understand their origin better. That's not a simple problem. We should measure one thing, but we're measuring all the parameters we can and trying to compare exactly what would spins be like if they were dynamically made or made in primordially or made by the collapse of the star and so forth. We don't have definitive results on any of that. But one thing that we are doing is looking at the almost 100 events or 70 or so events and looking at it, what we call exceptional events that don't really aren't just collecting data over this wide band, but are somewhat different. I'm not going to talk about them in detail, but give you because there's no conclusions. They're just events that are giving us hints at things or maybe not. We have events or an event that doesn't really fit the picture of a binary neutron star because it's 5 sigma higher in mass than you should get from a merger of the binary neutron star as we understand it. So maybe our measurements aren't good enough, but we think they are. But there's at least one example of that. We have an event that has the largest ratio. So one thing that's difficult for us is to do events that have a big ratio of mass difference between the two objects. It's a problem in numerical relativity. It's a limit in how well we can calculate things to do the templates. When the mass difference becomes big, the biggest one we've detected is a mass difference of 9. And that event happens to fall right in the mass gap between the highest mass that we should be able to see for a neutron star and being too low a mass to have enough gravity to be a black hole. That's thought to be 3.5 or so solar masses. So we have this region in between neutron stars and black holes that we have maybe a couple examples or hints that there may be activity there that we'll pursue as we get more data. On the other end, there's not supposed to be black holes that are too heavy, intermediate mass black holes. Yet we've seen the merger of 2 very heavy mass black holes, a 66 mass black hole and an 85 mass, a solar mass black hole, to make a total of 142 solar masses. That's the region that's not supposed to have any black holes, so we at least have one. That's the heaviest example we have of a black hole. These are, having 80 events total or 70, then these are the few events that basically don't fit the picture, and it's one direction that we're looking. Interestingly, if we look at 140, 150 solar mass black hole, we don't see, because it's so heavy, it barely gets into our frequency band. So we don't see the whole ringing that you would see before the merger. And so it isn't 100% clear that what we're seeing is a black hole. What you see is something that looks like just a little oscillation, but that's the merger part itself. So that what we're seeing is just the merger itself or something else. So we can't rule out, because we don't see the Inspiral, that when we have a 140 solar mass object, that it actually is some other, there's some other explanation. So let me skip this and move on. Okay, let me talk about the future a little bit. In the future, we're going to move on to 04. Again, Salvatore showed this plot, and that is as we move into 04, the slope changes again, and we should be, I think the increases that we expect in the coming run should happen. I don't think there's anything even as big as putting in squeeze light that we did in the 3rd run that we're doing for the 4th run. So it's more power in the laser, and it's more incremental changes. So I think we should reach this. We should be able to see close to 200 megaparsecs. We should get an event every couple days, and and we look further out in the atmosphere. So let me talk a little bit, in addition to what Salvatore did, about the next generation, and make just a few comments. I did a little bit in the question period. One obvious thing, I think all the ideas almost are incorporated in the European Einstein telescope, which was designed conceptually in 2011 and is changing some, but basically the basic concept was there in 2011. In 2011, we were not even allowed to think about a future detector in LIGO because the NSF had put a big investment in LIGO and they wanted us to concentrate completely on detecting gravitational waves. So not by lack of desire, but lack of ability to do it, we have only begun to look at third generation detectors after we saw gravitational waves. And so we're catching up in that. The most sophisticated work then has been done in Europe, and they have done a design which is the Einstein telescope. It'll evolve from this probably, but this is what was the basic idea that was presented and got, let's say, scientific credibility. It's costed at present time at $1.9 billion. So it's expensive, but let me not address that. It's deep underground. It has to be really deep because the main thing is to be deep enough so that any vibrations that happen near the Earth's surface don't propagate down. And that tends to be hundreds of meters, 300 meters or something underground. And so it's deep underground, not shallow underground, to get rid of noises on the surface. There's two sites in Europe, to put it, that they found, one in the border between Holland, Belgium, and Germany, but in Holland, and the second one in Sardinia. Presently they're carrying both of those, and we'll see what happens in the future. So they haven't picked one side. There's different pluses and minuses, as you can imagine, on those two sides. They're going to 10-kilometer arms. It's the shape of a triangle, which lets you run the beams both directions. This is a way to get some information on the polarization. Something we haven't done yet is measure the polarization of gravitational waves, which we should be able to do to some extent using LIGO and Virgo, but the data hasn't been good enough yet to do that. A big step mentioned this morning is to become cryogenic. In the advanced LIGO versions that we're looking at, the Cosmic Explorer, we're deferring the cryogenic part until that's solved. Problems of going cryogenic are simply, how do you take out the heat without shaking anything? First. Secondly, if you go to low temperature, how do you do the optics? Where you have, what's the right materials, the best materials for the test masses? How do you coat them so that they're coated well in low noise? It's a new regime that needs R&D to do that. So in our case, we've deferred that somewhat. And once you have a complicated thing like this, you can focus in on, say, high frequencies or low frequencies. So this is the design of the Einstein telescope, which maybe will evolve, covers all of these. You heard about the third generation Cosmic Explorer from Salvatore. And I mentioned there, for people who aren't there, that the problem is we can probably even find a site where the curvature of the Earth can be compensated for, and can make 40-kilometer arms instead of 4 kilometers, which gives you nominally a factor of 10 in sensitivity. But the cost driver is the vacuum systems themselves. We make it 10 times longer. About a third of the cost of LIGO was in its vacuum system. If we don't change the technology, then it becomes by a factor of 2 or 3 the dominant cost. And these are obviously expensive. So we are working hard on R&D, and I don't know how successful to be because it's more of R&D of engineering sort, to look at concepts to make a high vacuum system that isn't using all the expensive materials and so forth that are done classically. The big thing about going to the third generation, I think, is that this is from my standpoint, is that not only will we be able to do gravitational astrophysics, but start to be able to do cosmology with gravitational waves. That's illustrated in this picture here, whether it's the Cosmic Explorer or Einstein telescope. What's shown is what redshift you go out to for binary inspirals, whether it's neutron stars on one side or black holes. We'll be able to see black holes basically out to the edge of the universe or out to decent redshift. So one thing that we can look forward to, and I think is, to me, a big motivator of another generation of gravitational wave detectors of the LIGO Virgo type, is to start becoming start to be able to do cosmology. Salvatore showed this graph, but let me show it again. This basically shows the difference in LIGO and Virgo. On the left is the redshift, which basically gets to a redshift 1 or so. And what happens that we can get to redshifts of that are at least decent, approaching 10 to the 2, with either the Einstein telescope or the Cosmic Explorer. Just other things before I close. We heard about the Pulsar timing array this morning and talked about it in the session. I can't really add much to that here, so I took those slides away. The LISA, we also heard about this today, and it's on track. It has a wonderful feature that well before the project goes, they had a proof of principle, a pathfinder that was flown 2 or 3 years ago, that not only demonstrated what was being required by the funding agencies and by themselves, but managed to do much better than that and basically met the LISA requirements for the technology that they need to fly. So it's really an engineering problem primarily now, and maybe funding, but it, I think, is in good shape. I want to comment on the LISA itself. Then looks for heavier masses than LIGO. Shown here is its ability to take binary systems of other types besides black holes or neutron stars, follow them as they merge together in LISA, and emphasize that this meeting has been the S07 of the goals for LISA, and that is the understanding of the gravitational wave background and the ability of LISA to do that. And that was talked about. But also it was mentioned, and I want to mention it here, the mid-band in between. This is an opportunity that I hope will happen. There's no technical reason it can happen. Historically, it wasn't clear that we would detect gravitational waves on the ground before it was detected in space. Space missions ended up taking longer, which is typical. But and so the choice of frequencies initially for LISA had to do with known sources and so forth. And we end up with a gap in frequencies, almost 3 orders of magnitude or so between LIGO and LISA. And that midband, which has been talked about at this conference several times, is something that basically a lot of us feel needs to be covered. And we heard here the ability over many generations of doing a Japanese proposal, DECIGO, at this conference that could cover the band inside. And it's a good example of what can cover the band inside. There's also several examples in there's studies that have been done, which I'll show, and there's some examples in a proposal in China to do this in between region. So basically, that region, I show a graph here of the region in between a particular detector, but don't worry about which detector. I just grabbed a slide to show it, which shows the fact that each of these lines, which are gravitational wave signals that we've seen, can be followed by watching them at earlier times in between, as much as a year before, before they're detected on the Earth's surface. Of course, knowing that they're there earlier, where they come from, enables you to actually prepare for the final merger and be equipped to see what you want to see. So one obvious reason to cover the in-between band is to have an earlier view. Of course, a yet earlier one is LISA, but it's too early almost. The time before it, up till it is detectable on the Earth, can be done in satellite experiments that were covering the in-between region. So we did a study at my colleagues, was reported here by Yanu Chu and Simeon Bird and myself to look at this in-between region. And we made a little paper to see its ability to see to improve on several things, but we picked cosmic strings. And the little, I don't have time to go through it because I'm running out of time, but the little insets show you how much better you do if you add this in between detectors. So the ability to have the kind of detectors that are proposed in between gives you the ability to track events that are seen on the Earth and to do maybe a better job on, for example, searches for cosmic strings, which is from our article or from Earth thing. With that, I'll end. So thank you.
Okay, thank you very much.
Okay.
So we still got a few minutes in the schedule for questions or comments, if anybody has any. If Barry, you agree to take them?
Absolutely.
Don't see anybody immediately, so maybe I can ask my question.
Sure.
So you talked about LIGO and Virgo sending out alerts to the other types of astronomers. To what extent do you listen to the alerts coming from the other astronomers and look to see whether there's some effect in your data that maybe you might not have emphasized previously because you have to worry about a look elsewhere effect? But if you know when and where to look, maybe you can pick something out.
Yeah. So that's a good question, and let me comment. We don't have to do the same thing like turning a telescope or anything. So what we do is look at our data. One thing that we've done is, for example, look at gamma ray bursts. So when we look at we see the sky. So we look at when people look at gamma ray bursts and see, since we haven't seen them except for this one event, of course, but we don't see them otherwise, we can sum over some number we can all look within seconds or whatever time and see if there's any enhancement on tens of events or hundreds of gamma ray bursts that we've seen. So that's at least one example of us doing something where we do it statistically, and we're able to do it statistically afterwards. There's no reason to point, so we don't have that reason, but I think that's at least one reason to pay attention to what astronomers see and see if we, see something. I don't have another quick example, but that's the main one that we've done actively, is to look and see if we get any signal within some time band of when gamma ray bursts are seen. If you have any other suggestions, that would be good too.
Well, I know sometimes people talk about fast radio bursts, but they're probably not such dramatic astronomical events.
Yeah. But anyway, we do have the ability, we see the whole sky. So if there's anything astronomically that we should pay attention to beyond gamma ray bursts, we already are doing that.
Okay, thank you. Anybody? Yeah, Subodh.
Hi. Thank you very much for the very nice talk. I was wondering about. So I heard some years ago that there was possibility that, you know, once you start seeing many events in future generations of gravitational wave observations, that there is also the possibility of doing the same thing that optical astronomers do, which is to stack observations and maybe improve you know, signal to noise ratios that way for certain events. So do you know how viable that is, or how feasible that is, particularly for people interested in looking at maybe, you know, particular things at the ring down of merger events to look for quasi-normal modes and things like this? If you could.
Yeah, people talk about doing that right now. We're not static like a general astronomical or even an accelerator. We're kind of changing our sensitivity with time. So we're seeing, so our ability keeps growing and changing with time. So it hasn't been as good a tool as it might be if we're static for a while, I think, and we're just accumulating data. So it is something that we talk about, but it hasn't played a real role in the analysis. I mean, the only thing that we have now that has statistics are the black hole mergers, and of course those aren't seen by telescopes. So we don't really have a sample where it's played a big role at this point, but we're certainly aware of it. And it's a little bit like some of the other things I talked about that, you know, if we talk about before LIGO ever ran, there was a lot of things that we haven't gotten to yet because we've just seen this one.
Thank you.
Okay, perhaps I might ask a second question, Barry. So,
Sure.
close to the beginning of your talk, you talked about gravitational wave signals from neutron stars. I guess, you know, looking for rotating mountains on spinning neutron stars.
Yeah, right.
So there must be some ideas about how big those mountains could be.
Well, the thing is, we know that the problem. Let me repeat the problem that we have. Their mountains now we know are smaller than a millimeter, out of 20 kilometers or whatever size a neutron star is. Taking the known ones that we really understand. The trouble with those is they're incredibly mature. That's why you know the signal so well, and for radio signals so well. The ones that we know are not so, let's say, stable, are the young ones that are born after a collapse, because their frequencies change. So they're not detected by, they're not kind of in the catalog, let's say, of neutron stars. And they're the ones that are going to have a gravitational wave signal. So the dilemma that we have is our own problem, limited as experimentalists. And that is, if we look in the way we know how to look, which is look at known ones from in our galaxy from astronomical radio telescope observations, we're looking at the ones that are going to have the smallest effect. If we try to look at the ones that are, let's say, young, the problem is we have to do our own independent search. And that's a computing problem that we just aren't able to do. It's orders of magnitude beyond anything we're capable of doing to search the whole sky for young neutron stars. So we try to do it with the help of people's home computers and so forth, but we're orders of magnitude away from really being able to do it well. So that also hasn't gone very far yet. So as I said, personally, I always thought 10 years ago or so that was what we were going to see, but I didn't appreciate the problem that we have. We're just not very good at looking. So it doesn't mean that there shouldn't be gravitational wave signals. We have a kind of not very good way to match our information that we get from LIGO to a search mechanism that works.
Okay, thanks. So I see there's a question from Kostas Kordis.
Hi.
Yeah, hi. Thank you very much for the very nice, very interesting talk. I was wondering about those exceptional events. So if there is some understanding why one of the detectors saw a signal and not the other one. And so what are those?
There's no problem with that. That was one signal we generally One of them happened when one of the interferometers was down. We don't have anything where we actually have them running and one sees something, one doesn't. That hasn't been anything. That's the difference between the detectors is the fact that they're down. Let me comment experimentally what happens. Everybody's used an interferometer sometime in their college career. You went into a lab and used an interferometer and you looked and saw these fringes and stuff. So that what we do is what you call lock on a fringe. You have to keep it stable within one fringe, or you lose the ability to be an interferometer. And what happens is something happens. I don't care, lightning, truck rolling down the road, something inside the detector. We lose lock, meaning we're not on a fringe. That's an enormous experimental problem because maybe at CERN, you lose the beam, you can get it back in a short time. We have a real logistical problem getting back in lock. And so why is that? I mean, in the freshman or sophomore lab, you didn't have much trouble getting it. If freshmen can lock, why can't we? And the problem is that in the freshman or sophomore labs, you take these mirrors and you put them on an optical table and you make them stable enough so they're the same distance apart, and then you set yourself up, and within the wavelength of the light, you can see fringes. Our problem is that in order to isolate LIGO from the Earth, we use a combination of shock absorbers, which take care of the problem vertically pretty well, and make the mirrors on a pendulum. You've probably seen that in LIGO. We know if I hold a pendulum at the top and I move it, the bottom doesn't move very much. So the weight on the bottom doesn't move. So what we use to isolate ourselves from the motion of the Earth makes the problem very difficult. And that is that we use shock absorbers, we use that. So what happens is if we fall out of the wavelength because there was lightning or something, then what do we have? The starting position, we have a problem where the initial conditions are unknown. You have two pendula doing something. They may be wobbling, doing something to each other as an initial condition. So even though we have some algorithms and clever ways to try to bring it into lock, to bring them so there's some fixed distance apart, without understanding the initial conditions with all its motion, it tends to take I think on the average with a long tail, something like an hour. So and it can take many hours. So the problem is that then we're doing a triple coincidence, between two LIGO detectors and the other one. So if we're 80% of the time up, or 90%, it's 0.9 to the cube to get them all three to give a triple coincidence. And so for us, roughly in the last data run, the total average calendar time that all three detectors were in lock and running was only 50%. That seems low, and it is, because it's 0.8 something cubed. So even though they run at 80 some percent, and we should do better, but it's a hard problem. It's one or more of them being down when we observe an event is common, unfortunately. And so that's all you're seeing. And that happens to be true on the event you're looking at.
Thanks. Can I ask another question, or is there someone else who wants to ask?
So I didn't see anybody else. So Kostas, why don't you go ahead? Maybe we'll make that the last question. Okay.
So my other question is regarding measuring the polarization. So what are the prospects of maybe if there are any other types of modes?
I think the first measurement of the polarization is still a little ways off. And the reason is the following, that it takes, you have to have, you have the two polarizations at 45 degrees from each other. And so to do that, we have to have multiple detectors. And we made a decision in LIGO, which probably a theorist wouldn't like, but an experimentalist like me insisted on, which is we made the two interferometers in LIGO as parallel to each other as we could within the 16-degree curvature of the Earth. That paid off for the very first event, because when you saw it, you kind of believed it, because we saw the same signal in Hanford as we saw in Livingston. If they had been rotated 45 degrees from each other, we don't know what we would have expected in the two cases, because they had different, because they would measure a different part of the, polarization would be different. So we made a decision that would make the detection of a gravitational wave the most reliable, even though we gave up some physics in it. So we rely, just the way LIGO is oriented, on a third interferometer to be tilted enough from us to be able to tell. And that's Virgo. And we knew that, of course, from the beginning. The problem right now is that Virgo is not, it's one of the places we're paying a price for Virgo not being as sensitive as LIGO. So it's great for helping us do sky location, but it's still a factor of 3, which means for most events, since it's, it goes as the cube, we're not getting a very big signal to noise signal out of Virgo, and so we're not able to do it yet. It'll happen, but that's the limitation at the present time, just a very practical one because of the way things are working. I think it should happen as Virgo increases its sensitivity. They're not catching up because we keep increasing LIGO, so they make a step to where we were rather than where we are. And so it's probably another few years before they're together, but maybe I don't know, maybe we'll get lucky that there's an event that's close enough to Virgo that we can tell, but that's the problem. So it's a silly experimental problem, but there's a history in why we did it that way.
Thank you very much.
Yeah.
Okay, so thanks again, Barry. Really appreciate your big overview and your wisdom. So thank you very much for your talk. And I'd just like to hand over for some closing remarks to Anish Ghoshal, one of the, I would say, the principal organizer.
You're muted.
Anish, you're muted.
Sorry. Yeah. Sorry. Thank you. I won't take much time. I just wanted to say a couple of words to formally close the nice program that we had a week long. So some of the recordings of the talk individually will be available on YouTube. We have live streamed all of the sessions starting from day 1, 2, 3, 4, and 5. So the live stream recordings of all the talks are already available, and individual talks will be put on YouTube very soon. We gratefully thank all the speakers who spend their time to prepare the talks and presented in our week-long workshop and made the workshop successful. We thank all the chairs of the sessions, and we thank all the panelists, including the speakers and the panelists who were not the speakers, to have spent their time and made the discussion sessions lively. And we also thank the panel discussion leaders who made the program much more enjoyable and raised very interesting questions throughout, not only the talks but also during the panel discussion sessions. Then I would like to thank my fellow co-organizers. I know for all the speakers and the panelists and the discussion, you have been receiving emails from me, but it is, I mean, just receiving emails from me and communicating with me. But all my fellow co-organizers, John, Kaiser, Nobuchika, Marek, Bogumia, they worked very hard to throughout the course of the last 3-4 months during the time when I was communicating with you, to make the program a successful one, and helped me with all the advices at each point of time regarding the logistics and also regarding technical details in order to make the program reach to you. Finally, a couple of points regarding the fact that we missed many topics. We might have missed many top topics, many interesting talks because of the shortage of time and because of the time zone problem. We could not have kept the program for a longer duration. We should surely plan to have some discussions over those topics that we might have missed. We had over 500 registered participants, and many people registered and also attended from many remote places, which I think otherwise would not have been possible had it been not online. So that is one of the, I think, upside of having a conference or a discussion session online. So what this means is that we should have some future activities. So I would request my co-organizers to have some plans. Maybe next year we can have some future activities, maybe in the same settings or some hybrid settings. So surely we want to plan something future, given the interest of so many people and given the fact that there are many more interesting prospects that we can have discussions on, and many interesting future prospects that we saw in the workshop. And then finally, regarding if any of you need any more information on logistics regarding this current workshop, don't hesitate to contact me. My email address is there on the website, and I will be happy, and also my fellows will be happy to provide you any logistics that you might need. Thank you, and we closed our week-long program here. Hope to see you guys soon again, sometime.
Thanks, Anish. But before we go, maybe this is a good time to, from the other organizers, to point out that it is, well, as John hinted, it was Anish who did most of the heavy lifting in organizing of this conference, and without him, the meeting would have not been possible. So let's thank him again. Thanks, Anish.
Thank you. Ciao.
Bye. Ciao.
Thanks everyone for the nice meeting.
Thank you, everyone. Bye.
Bye.
All right, thank you.
Ciao.
Sorry. Soon, I hope.
Bogomia, you're up. You said you have, maybe it's very late for you, right?
Yeah, I managed to put my daughter to sleep at the very beginning of the lecture, so
that's nice.
So I came here.
That's nice. That's nice.
Yeah, and I hopefully you will be able to get to Warsaw soon, so meet you in person. Hopefully, see you guys in person soon.
Yeah.
Would be nice.
So, yeah, thanks for the week.
Yeah, thank you very much, and
Yeah.
hope to see you in person soon. Bye.
Yeah, that would be nice.
Yeah.
Let's have some rest. Bye bye.
Yeah, bye.